Annenberg Media.
That was great. Thanks a lot. You really make that look easy. You don't learn to play the sax like that overnight. It takes years of practice, starting with simple pieces and moving on to more complex ones. There's an algebraic equivalent to writing and playing beautiful music. It's the creation and solution of equations. Equations are the songs of algebra, and that's what we've been working toward in the past 4 programs. Thus far, we've learned about the parts of equations, things like radicals, exponents, and polynomials. Learning how to factor, simplify, and work with these parts is essential, but it's a little like practicing scales when you're learning an instrument. In this program, we're going to move on from mathematical scales to real music, the music of equations. We'll learn about the simplest kind of algebraic equations, linear equations. We'll learn how to solve such equations for an unknown variable, and we'll see how to check that we got the right answer. Finally, we'll learn how to apply these skills to solve the kind of problems that crop up in real life. Equations are the lifeblood of algebra, and learning to solve equations is one of the central skills we'll use throughout this series. We'll learn the basics of equation solving by working with equations like this: 2m plus 3 equals 7. Notice that this equation has only a single variable m, and that the variable is raised to the first power. All such equations are called linear equations. Now, what does this equation say? Well, it says that 2 times some real number m plus 3 equals 7. Now, even if you didn't know much about algebra, you'd probably be able to solve for m. That is, find the value of m that makes the equation true, with a little mental trial and error. You'd probably puzzle over it for a second, try a few numbers in your head, and fairly quickly realize that 2 fits the bill. 2 times 2 is 4, plus 3 equals 7, 7 equals 7. It checks. This kind of intuitive approach is okay for simple equations, but we can get bogged down when the equations get more complex. That's why mathematicians have devised some basic techniques for solving equations. With only a few of these under our belt, we'll be able to solve any kind of linear equation. The bedrock principle of solving equations is this: as long as we do the same thing to both sides of an equation, we don't change the value of the variable that makes the equation true. For instance, let's start with the equation we were just working with. Let's try multiplying both sides by 100. Distributing the 100 and multiplying gives us 200m plus 300 equals 700. Remember that we figured out that m was 2? Well, substituting 2 again, we see that it still works. 200 times 2 is 400. Adding 300 gives us a true statement. 700 equals 700. Now, in addition to multiplying by 100, let's try adding 725 to both sides. You can see that our humble equation is looking more complex. Once again, however, adding something to both sides doesn't change the value of m that makes the equation true. Substituting 2 still produces a true statement. $1,425 equals 1,425. This idea that we can perform identical mathematical operations to both sides of an equation without changing the sense of the equation is the key to solving them. To see how this works, we'll start with our newly complex equation. We'll pretend that we don't know the answer and solve it using the rule we just learned and our previous knowledge of simplifying polynomials. When solving an equation for an unknown variable such as m, the first things to tackle are all operations involving parentheses. So here that means distributing the 100 across both the terms in the parentheses. Now we can combine like terms on both sides of the equal sign. Next, we want to get the variable term on one side or the other of the equation. In this case, we can do that by subtracting 1025 from both sides. This leaves us 0 as a remainder on the left side and 400 as a remainder on the right. Now, since we want to find out what m is, we try to get it alone on one side of the equation. So we can now divide both sides by 200. That way, the 200 on the left simply becomes 1, and the right-hand expression reduces to 2. We're left with m equals 2, the same answer we figured out in our heads at the beginning. Now let's use the rules we've learned to solve an unfamiliar equation. Step 1. Clear the parentheses using the distributive law. Now step 2. Combine like terms. Step 3. Get the variable on one side of the equation by performing the appropriate additions, subtractions, multiplications, or divisions on both sides of the equation. Here that means adding 18 to each side. Step 4. Isolate the variable, again by performing the appropriate operation on both sides of the equation. In this case, we need to divide by 8. The number that satisfies this equation is 3. You can see how a seemingly complex equation can be quickly cut down to size by combining like terms and using some basic algebraic rules. Now, one of the nice things about solving equations is that you get to be absolutely certain you're right. You can always check your answer by substituting the value you find for the unknown variable back into the original equation. If the two sides turn out to be equal, you know your answer is correct. Let's try checking the answer we just found. We'll substitute 3 into our original equation. Now it's just a matter of arithmetic. The equation checks. We know our answer is correct. Now we know the basic steps in solving linear equations. Clear the parentheses, collect like terms, get the variable on one side of the equation, isolate the variable, and check your answer. In addition to these basic steps, there are a few other techniques that come in handy when solving linear equations. Here's one to use when you run across an equation with decimals. Equations with decimals are easier if you eliminate the decimals first by multiplying by the appropriate power of 10. In this case, since the decimals are in tenths, we only need to multiply both sides by 10. Now we can clear the parentheses, add 36 to each side to get the variable on one side, and divide both sides by 12 to isolate the variable, leaving us with our answer, y equals 5. It's also very common for linear equations to contain fractions, such as these. Now, as with equations with decimals, these equations are easier if we first clear the fractions by multiplying both sides by a common denominator. In this case, the least common denominator is just the product of the denominators, 28. Now clear the parentheses by multiplying through by 28, and simplify the resulting fractions. Now isolate the variable by subtracting 20k from each side and adding 7 to each side. It's worth mentioning here that it doesn't matter which side of the equal sign you decide to get the variable on. It's really just a matter of convenience. For instance, in this equation, we could have just as easily subtracted 21k from each side. It's 21k minus 21k, which gives us -7 equals -k plus 8. Then we want to get the variable alone, subtract 8. We get -15 equals -k. But we're not asked to solve for -k, we're asked to solve for k. So multiply both sides by -1, 15 equals k, which is just what we got before. Thus far, we've learned how to solve linear equations. We've seen how the principle of doing identical operations on both sides of an equation lets us simplify and solve equations. And we've learned a few techniques to help us solve decimal and fractional equations. But the real point of learning algebra isn't just to be able to solve equations given to you in a book. Algebra is used to solve problems out there in the real world. And the real world doesn't arrange itself neatly on a page with equal signs, variables, and polynomials all set up and ready to go. We need to be able to create our own equations, compose our own music, if you will. We need to be able to translate messy and sometimes confusing situations into algebraic terms. Then we can use the skills we've learned to solve the equations and find a solution to the problem. For instance, here are two situations in which algebra is crucial.
How can you count the number of fish in a lake? For wildlife biologists on Lake Winnipesaukee in New Hampshire, that's a serious question. The smallmouth bass population here has been under pressure from increasing numbers of fishermen. To regulate that pressure, the state needs to estimate the bass population. That estimate is obtained using algebra and data from a bass tagging program. Underwater nets are used to catch bass in selected sites across the lake. The bass are separated from the rest of the fish caught in the nets. A careful record is made of each bass caught. The fish are measured,
360,
weighed,
1 pound, 6 ounces.
Should be tagged.
and harmlessly marked with a numbered tag.
Yep. Pretty fish.
The tagged fish are then released, free to mingle with the rest of the untagged bass in the lake. At a later date, this process will be repeated. The biologists will count the total number of bass and the number of those bass that have been tagged. How can this information be used to estimate the entire bass population of the lake? A modern sewage treatment plant is a maze of pipes, pumps, valves, and tanks. This plant outside of Los Angeles handles about 60 million gallons of raw sewage every day. Because the volume of sewage varies from day to day and from hour to hour, the flow through the tanks and basins must be constantly adjusted by opening and closing valves. These giant tanks, for instance, hold millions of gallons of sludge, the solid that remains after sewage has been settled. Inside the tanks, bacteria convert sludge into methane gas, which is diverted and used to produce energy. Because there are usually several inlet pipes to each tank, maintaining the proper level can be tricky. Suppose that a digestion tank has two inlets, one which can fill the tank in 10 hours, and the other which can fill the tank in 12 hours. A plant worker discovers that someone has left the first pipe on for 5 hours without turning on the other one. Now he needs to know how long it will take for the tank to fill if he opens the other pipe too.
To solve these and many other real-world problems, we need to translate the situations into algebraic statements. Learning this skill is just like learning to play an instrument. You start small, practice, and before you know it, you're a musician, or in this case, an expert in equation solving. It's because it helps to start small that sometimes you encounter problems like these in algebra texts. If Sam is twice as old as Harry, and the sum of their ages is the same as 5 times Harry's age, decreased by 28, how old is each one? Well, you know and I know that the smartest way to answer this would be to just ask Sam and Harry how old they are. But that's not the point. Questions like these give you a chance to sharpen your skills in translating words into equations. They're a warm-up for more realistic problems. In fact, let's just solve this problem as a way of getting our feet wet in the world of word problems. The first thing to do with a word problem is to read it slowly and carefully. Reading it twice helps us grasp the situation and visualize it in our mind. It's also sometimes helpful to sketch the situation. Here, the only things in the sketch are Sam and Harry. The second step is to describe the parts of the situation with numbers and variables. We use a variable to describe a quantity that we don't know and want to find. In this case, we don't know either Harry's age or Sam's age. It would seem logical then to use one variable to represent Harry's unknown age and another variable to describe Sam's age. Well, we could do that, but then we'd have two different variables to work with, and that would make for a complex equation, and one we haven't yet learned to solve. So instead of using two variables, we need to figure out how to describe the situation with a single variable. Let's start by representing Harry's age with the variable a. As you work, be sure to write down your variables and what they stand for. Now, is there any way to say what Sam's age is relative to Harry's age? The answer is in the problem. It says, if Sam is twice as old as Harry, so we know that no matter how old Harry is, Sam is twice as old. That means we can represent Sam's age as 2 times Harry's age, or 2a. Now we're making progress. We've already begun the translation of this word problem to algebra. We've represented the parts of the situation with numbers and a variable. Now we need to create an equation so that we can use our algebraic skills to solve for the unknown variable. Once again, the clues for this lie in the problem itself. We're told that the sum of Harry and Sam's ages is the same as 5 times Harry's age decreased by 28. So let's take that one piece at a time. What is the sum of Harry and Sam's ages? Well, using the scheme we've just created, that's a plus 2a. Then we're told that this quantity is the same as something else. So we can write that a plus 2a equals something. That something, we're told, is 5 times Harry's age decreased by 28. 5 times Harry's age is just 5a. And decreased by 28 means that 28 is taken away or subtracted from that quantity. So the right side of the equation can be represented as 5a minus 28. Now we have something that looks familiar. We have an equation with a single unknown and some numbers, which we know how to solve. First, we can combine the two a terms on the left to get 3a equals 5a minus 28. Then we can get the a terms on one side of the equation by subtracting 5a from both sides. Now we can isolate the variable by dividing both sides by 2. Finally, we multiply both sides by -1 to get the variable positive. Now, if this was just a problem in a book, we'd be all done. Our answer would be a equals 14. But since this is a word problem, we still have another step, interpreting our answer in the terms used in the original problem. This interpretation is relatively straightforward since we've already decided what the variables stand for. A is Harry's age, so Harry must be a lad of 14. And Sam is twice Harry's age, so he must be 28. Maybe he's Harry's older cousin. As silly as these problems are, they make some sense to work on. They prepare us for the kind of problems encountered in the real world. The steps we used here can be applied to any word problem and are very important. Read the problem slowly and carefully. Sketch the situation if that's appropriate. Describe the parts of the situation with numbers and variables. Use the information in the problem to create an equation. Solve and check the equation using algebraic techniques. And interpret your answer in terms of the original question to see if it makes sense. Now let's use these steps to solve some more realistic problems. Let's look at the fish problem first. Remember that the wildlife biologists were trying to find out how many smallmouth bass are swimming around in Lake Winnipesaukee. They tagged 200 fish, released them, and caught another 200 fish a month later.
And that's what we're after right there. Smallmouth bass.
In the repeat sample catch, they find that 3 of the 200 are tagged. How can we now figure out the total fish population? Let's write down what we know. We know the number of fish the biologists tagged, 200. We know the number of tagged fish in the sample they took 2 months later, 3. And we know the total number of fish in that later sample, 200. Now, what's our variable? Well, it's what we don't know, and we don't know the total number of fish in the lake. So we'll use F to stand for the total fish population. The key to creating an equation with this information is recognizing that this is an example of a proportion problem. A proportion is a special form of equation that relates two ratios. The general framework is that A is to B as C is to D. The A over B fraction is one ratio, the C over D fraction is the other ratio, and the equation as a whole is a proportion. So how's that work in our fish problem? Well, we know that 3 of the 200 fish caught in the sample were tagged. So this ratio, 3 over 200, is representative of the proportion of tagged fish in the lake. Since we know that there were 200 fish originally tagged, we can set up a proportion. 3 is to 200 as 200 is to F, our unknown fish population. Now we have an equation we can solve. Since it contains fractions, let's eliminate them by multiplying through by the common denominator, 200F, and reducing the resulting fractions. Dividing both sides by 3 leaves us with F equals 13,333.33. We said that F was our estimate of the total fish population in Lake Winnipesaukee. Since we found that F equals 13,333.33, that's about how many bass are in the lake. Now, this is a good example of why it's important to interpret the answer to your equation in light of the original problem. Obviously, we don't expect to find 33/100ths of a fish swimming around in the lake. So the real answer to our problem is 13,333 fish, more or less. Not the more precise but meaningless 13,333.33 fish. Now let's go back to the situation at the sewage treatment plant. The problem involves the giant sludge digestion tanks at the Los Angeles sewage treatment plant. One of the tanks has 2 inlet pipes, one that can fill the tank alone in 10 hours and another that can fill the tank alone in 12 hours. A worker discovered that the first pipe was turned on for 5 hours and now needs to know how long it will take for the tank to fill if he opens the second pipe as well. This is a variation on a class of word problems called work problems. The key to solving them is to look at how much of the situation occurs in a single unit of time. Usually that's hours. For instance, in this problem, we know that the first pipe can fill the tank alone in 10 hours. That means that in a single hour, the output from this pipe fills 1/10 of the tank. Likewise, the second smaller pipe can fill the tank in 12 hours. So in a single hour, that pipe fills up 1/12 of the tank. Now, since we don't know how long it would take for both pipes working together to fill the tank, let's call that X. So now we have the ingredients for the equation. Finding that equation takes a bit of thinking about the relationship between the parts. At this stage in the game, it's sometimes helpful to play with the problem a bit. Try playing out different scenarios just to see what happens. For instance, we said that the total time to fill the tank is X hours. So how much of the tank is filled in a single hour? Well, suppose for the sake of argument that it took 20 hours. Then in each hour, 1/20th of the tank would be filled. So if it takes X hours, then 1 over X of the tank will be filled each hour. This is the crucial insight for this problem, because now we know 2 quantities that are equal to each other. We said before that the first pipe fills 1/10 of the tank in an hour, and the second fills 1/12. If both are working together, then the sum of these 2 rates equals 1 over X, the portion of the total filled in an hour. So we can write our equation this way. 1/10 plus 1/12 equals 1 over x. To solve the equation, we multiply both sides by a common denominator, such as 120 times x. This eliminates the fractions and gives us 12x plus 10x equals 120. So that's 22x equals 120. Dividing both sides by 22 leaves us with 5.45. So if both pipes were open, it would take only 5.45 hours to fill the tank. That's valuable information, but it doesn't answer our original question. Remember that the first pipe was left open for 5 hours already. What we need to know is how long it will take the tank to fill if the second pipe is now opened. Well, now that we know the rate at which the tank would fill with both pipes open, we're in a good position to solve the problem. If the first pipe was on for 5 hours alone, then we know that 5 times 1/10 of the tank is already filled. That's 5 over 10, or a half. So by the time the mistake is discovered, the tank is already half full. So now only half remains to be filled. Since we know that with both pipes open, the entire tank will fill in 5.45 hours, it will take half as long to fill half the tank. So half of 5.45 hours is about 2.73 hours. That's roughly 2 hours and 45 minutes. In other words, the tank's filling fast, and the worker had better not take a long lunch break. These problems show how basic algebra can solve some important problems in the real world, problems that can't be solved any other way. They also show that the solution of word problems involves more than just skill with the mechanics of algebra. You often must recognize the pattern of a problem and be able to use the appropriate formula or relationship to solve it. By learning to translate real situations into the language of algebra, we've taken a major step. We've learned how to solve problems by creating our own equations and solving them using the rules of algebra. In other words, we're on the road to becoming as adept at algebra as Herman is at playing the sax.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.